Tutorial 10. Now in the tutorial 10, you need to implement three functions. Okay, the first one is to test if a binary tree is strictly binary. Now, so whenever you implement a function, first of all, okay, read the requirements, okay, the definitions carefully, okay, and then you start to think about how to organize your program. Well, once again, in today's tutorial, my program students, they try to implement some of the functions, but they don't read the requirements. Okay. So now, okay, coming back to the last tutorial, okay, the first function is to test if a binary tree is strictly binary. Okay, now the definition of a strictly binary tree is that all the nodes in the tree have the degree either equals to 0 or equals to 2. Okay, so it means that there's no nodes in the tree with degree equals to 1. Okay, so this is the requirement. So when you write the programs, okay, many of you still like to think about the programs, say considering that if you have receive a pointer, okay, and then you consider whether this node, the root has a right child and a left child. Okay, so you come up with 4 different combinations. Okay, no childs at all, both childs are present, have the right child, don't have the left child, have the left child but don't have the right child, so on. Okay, so try to, before you start to type, okay, try to think about the problem first, and whenever you come up with some program structures that looks pretty messy, then it's time to rethink about it. Okay. Now, according to the problem requirement, okay, we need to determine the degree of a node in the tree. Now, in any recursive functions that we apply to a binary tree, as I have repeat mentioning this idea many times. So when you design a recursive function, okay, that operates on a binary tree, then within this function, okay, basically you see 3 components in the binary tree: the root, the left subtree, and the right subtree. Okay, you don't need to say within your recursive functions you try to traverse the tree, okay, into deeper levels. Okay, this in general will not be a correct approach. Okay, now to solve the problem whether or not a binary tree is strictly binary, okay, we need to find out the degree of the nodes. Okay, now in the current level of recursion, we only consider the root. Okay, the degree of the root. Okay, so instead of coming up with many different combinations of the left pointer is now, left pointer is not now, and then the right pointer is now, right pointer is not now. Okay, the first thing you need to do, in fact, is to check if the pointer that you receive is a null pointer or is it not a null pointer. Okay, so if it is a null pointer, you have the answer. Okay, you don't need to do further computation, you have the answer. Okay. Now if it is not a null pointer, okay, then you need to find out what is the degree of the root. Okay, now the value, the variable degree is initialized to 0. Okay, then if the p is a null pointer, then we don't do further changes to the variable degree, then it has the value 0. Okay. Now if the tree is not empty, okay, then we check whether or not the root has a left child. So if the root has a left child, then the degree of the root is increment. Then we do the same to the right pointer. So if the root has a right child, then the degree is increment again. Okay, so you don't need to have a nested else type of statement. Okay, now after determining the degree of the root, then you can answer the questions whether or not the tree is strictly binary. If the degree is 0, okay, it means that you have reached a leaf node or the tree is empty. Okay, then this subtree is strictly binary. Okay, you don't have other things to consider. Okay, or if the degree is not 0, okay, then you test for the second condition. Okay, then the degree must be 2. If the degree is not 2, then it is 1. Then it's not strictly binary. Okay, so if degree is 1, then the remaining part of the statements will not be executed according to the convention in the C language. Okay, so whenever in a logical statement, okay, the evaluations, when you are using a conjunction, if the evaluations of the preceding part is already not true, then the remaining part of the statement will not be evaluated. Okay. Now, if degree is 2, then the tree is strictly binary if the 2 subtrees are also strictly binary. And you don't need to have very complex statements. Okay? Now, the second part of the exercise, okay, this part is included mainly to help you to solve, okay, the third part, because the program structures of the 2 functions are basically the same, okay, with the exceptions that the operations, when you are dealing with the recursions and also the operation dealing with the root is slightly different, but the structure of the function are the same. Now, in the print leaf function, we want to print the leaf nodes, okay, from left to right, okay, in the tree, basically. Okay, so if you are going to print something from left to right, then it means that whenever you make a recursive call, you process the left subtree before the right subtree. Okay, then the things will be output, okay, from left to right. Okay. Now, once again, if you are asked to print the leaf nodes of a subtree, the first thing you do is to check if the pointer P is a null pointer or not a null pointer. Now, if it is not a null pointer, you don't need to do other things, you simply return. Now, the function is defined to have a void return. Very interesting. One student mixed up, okay, a function have a void return, whether it return or not return. Okay, a void return means that the function will not return a value, but the function, of course, must return. If it doesn't return, then the user will not see your program to terminate. Okay, either you have infinite loop or infinite recursion, then your program won't return. Okay. Now, if the pointer P is not a null pointer, then you may need to do something. Now, since we only need to print the leaf node, okay, then we can perform a test to see whether or not the node P is a leaf node. If it is a leaf node, then we do the printing. Okay. If it is not a leaf node, then we make the recursion. Okay. And in calling the function recursively, we handle the left subtree before the right subtree. Okay. Now this is the general structure. Now then, to print the Hoffman codes. Okay. Now you see the program structures is the same as the printf function. Okay, so we test if the tree, the pointer, is a null pointer. If it is null pointer, no need to do anything. If it is not a null pointer, we check if it is a leaf node. If it is a leaf node, okay, do the output. Otherwise, okay, you make some recursive function call. Now to print the path, then okay, when we are moving down from the root to a node, we remember the path. Okay, we save the path into the character array, and the integer parameter k represent the path length for arriving at the node P. Okay, so how many steps we have taken when we arrive at the current node. Okay. Now if the current node is a leaf node, we print it out. Now to print out the path in a character array, okay, we can use a small tricks. Okay, we append the end of string symbol, okay, to the path. Then we can simply use the standard insert operators to print out the whole array. We don't need to write your own for loops to control the output of the characters. Okay, so here we put the end of string symbol at the end of the path, then we simply send it out. Okay, because these operators will do the printing until it sees the end of string symbol, then it stops. Okay. Now if it is not a leaf node, if node P is not a leaf node, okay, then okay, we are going to make a recursive call, okay, to move down to the left subtree and also to move down to the right subtree. Okay. Now if we are going to move to the left hand side, we are taking the steps with the value 0. So we put the value 0, the character 0, into the path, and then we make the recursion, we increment k. So we take one more step when we arrive at the next node, okay, the child of P. So when it return, okay, when this, okay, recursion return, coming back to the current level, so it means that we have already printed all the leaf nodes, okay, in the left subtree. Now we try to move to the right hand side. So when you move to the right hand side, you change your steps from 0 to 1. Okay, and then you make your recursion and increment k. Now in general, many of the recursive functions that we write for manipulating a binary tree are not long. Most of the time will be less than 10 lines of statements. Okay. So if you I think it will be the same in the exam. If you come up with some answers with more than 15 lines of code, then you are thinking in the wrong direction. Since it looks like that we are moving, okay, the pace of the lecture is doing fine, and we still have some time, and we can afford to do a bit more discussion. Now, last week we have talked about the reconstructions of a binary tree from the p-order and in-order sequence. So you all understand that process. Now what if we want to write a program to do the work? Don't think that the program is complex. It's also a few lines. Now, before I show you the program, or I work with you to go through the steps. So let's once again go through, the reconstructions algorithm. Using paper and pen. And the assumption we are making, in the design of the program, to simplify the work, we assume that the input sequence are weighted, meaning that there will not be errors in the input in order and p-order traversal sequence. Now to do the reconstruction, what we need to know, when we are dealing with the reconstruction, what we need to know. Now at the beginning, we need to know the range of the sequence within the in-order traversal. So based on this sequence, we are going to reconstruct a tree, right? So we need to keep a pair of index to let the program to determine what to do. So let's say we have the start index for the in-order sequence and the end index for the in-order sequence. So similarly, we have the start index for the p-order sequence and the end index of the p-order sequence. Now, based on these two pair of sequences and the character array, what we are saying here is that from the start index of the p-order sequence, we know the label of the root. Knowing the label of the root, we go to the in-order sequence. Find out its position. So we know his index in the in-order sequence. Now, what is the next step? Now, finding out the index of the root, then the program will create a note. Save the label. Save the label into the root. And then we construct his left subtree using recursion. Now, to reconstruct the left subtree using recursion, what will be the required information in the next level of recursive call? We need to know the start index and the n index, okay, of the in-order traversal sequence in the recursive call for the construction of the left subtree, right? Okay. And after we have created left subtree, then we will reconstruct the right subtree using the same method. Okay. Now, when we are dealing with the left subtree, then what is the corresponding pair of index in the p-order sequence? So this will be the new pair of index, okay, in the p-order sequence. Okay. Now, what is the start index of the left subtree in the p-order sequence? The start index will be the original start index plus 1, right? Then what is the n index? The n index will be the original start index plus the size of the left subtree. Then what is the size of the left subtree? The difference between these two values tells you the size of the left subtree. Okay, so we can derive all the informations, okay, in the current level of recursion, and then you make the recursive call to reconstruct the left subtree, and then, okay, to reconstruct the right subtree. Okay? Okay. Now, let's, okay, work through the program. So when you design the function, so what's the first thing to do? You need to decide on the interface. Okay, now you are going to construct a tree. So what is the return value of the function? It returns to you a tree not pointed. Now, there are some field tree functions given to you in the tutorial exercise, but in the exercise for convenience, we use an array representation of the tree. Okay. Now, in the field tree function, it will return, okay, a tree not pointer. Then what are the other input parameters required? Okay. Now, you will require the in-order sequence, right? Okay, so it's a character array. You need to know the start and end index, within which part of the character array I'm going to reconstruct a tree. Okay, so we need the start and end index for the in-order sequence. So we have the suffix I. Okay, that is for the in-order sequence. Then we also need the p-order sequence. Okay. Let's put it on the next slide rather than having it very long. Okay. And we need the start index for the p-order sequence. Now then, how about the n index of the p-order traversal? Basically, we don't need it in the program because in the reconstruction process, you see that we make use of the start index of the p-order sequence to find out who is the root. Other than that, we don't need to know who is the last element in the p-order traversal. Okay. Now, the assumption is that the input traversal sequence are consistent. Okay, so we don't require in the program the n index. Okay, for the p-order traversal. So we left it out. We don't require that. Okay. So in the main function, okay, so when we the field tree function for the first time, we pass to it the in-order traversal sequence, the p-order traversal sequence, and initially it covers the full array of the in-order. Okay? And also the first node, the start index for the p-order sequence in the same range as also the start.
You can't really see it in the screen. In the full screen.
Sometimes the projector is not properly aligned. So thanks for alerting me, but how come all the others keep quiet? Or you can see some other characters outside? No, it's not there. Okay. Now in the main method, okay, what are the you have the in-order array, you have the p-order array, okay? And then when you make the first call, this is the range for the in-order sequence. And the start index for the p-order is also the first symbol. Okay? Now, within this recursive function, every time we write a recursive function, the first thing we consider will be the base case. Okay, so what will be the base case? The base case usually is the case that you don't need to do anything. And it's the base case. Okay, so under what condition you don't need to do anything? If the start index of the in-order traversal sequence is greater than the end index, then you have nothing in the range. And the tree is empty. Okay, you don't have anything to do. You don't need to do anything. Now, if it is not empty, then you need to do some work. Okay. So what's the work you do? The first thing is, what is the root label, right? Okay. Now the symbol at the start index of the p-order sequence is the root. It is something that, okay, you know from the explanation of the reconstruction process. Now, knowing who is the root, then what's the next step? Find out the position of the root in the in-order sequence, right? Okay, so to find out this, we need a variable, okay, to represent the index of the root. Okay, so we are doing a searching. Okay, so we start from the beginning of the in-order traversal sequence, and we want to find out where is the position of the root symbol. So, as long as the value at the root index is not the root symbol, you move to the next label. And the assumption here is that can always be found. Okay, if it cannot be found, then it means that the input is not consistent and it does not fulfill the precondition requirements. Now we have found the root index. And what's the next steps? Create a node. Okay, store what? Store the root symbol to the root. And what's next? You reconstruct the left subtree and then you reconstruct the right subtree. Okay, now making a recursion. What are the parameters? In order sequence, start and end of the left subtree. Okay, so what are the start and end of the left subtree? Original start, root index -1. P-order sequence. Okay, what is the start index of the p-order sequence for the left subtree? The original start index +1. Okay, because the label at the start index has been consumed. Now you have reconstruct the left subtree. Then what's next? Right subtree. Okay, now call the function recursively. What are the parameters? What is the start index? What is the end index? The original. Now, if the right subtree is empty, then root index +1 will be greater than the end index of I. And in the recursive call, it will return to you a null pointer. Then the left right subtree is empty. Then what is the start index of the right subtree in the p-order sequence? Now it looks a bit long, right? Okay, so let's take out this part. Okay. Now this is the size of the left subtree. Root index minus, okay, start I. This is the size of the left subtree. And the start index of the right subtree in the p-order spiral sequence is the start index plus the size of the left subtree +1. Okay. Now you have complete the creation of the tree, finally. Okay. Now that's the complete program. Not compass, right?
For the second last line, it should be size SD.
Oh, sorry. The last option. I do some mistyping. So, what I'm trying to tell you here is that when you solving a problem, okay, don't try to start typing. You need to, okay, have a very clear picture. What are the parameters and the variables that you need to maintain in your functions? Okay, how to use them? Okay, what are their meanings? What you need to derive? Okay, so you have a clear idea. Then you start to type. If you start to type your statements without a clear idea what you need to do, then the more you type, the more difficult will be your task. Every time you put in something that is incorrect or irrelevant into your program, it makes your work more difficult. Okay. Try and error types of approach to solve a problem usually does not work in programming. Okay. And if you spend a bit more time to figure out what you need to do, then you will find out that actually the overall time that you spend to solve the problem will be shorter. And also, you need to somehow modify your way of thinking. Okay, when you write your programs, okay, don't every time when you are, say, having 4 possible cases in front of you, then you start to write your programs that I have 4 combinations. Or if you have 8 combinations, then you start to write your programs that you have 8 combinations. Usually, if you do it this way, then you will get stuck in the future that you will be able to solve problems that with up to 4 combinations. More than that, you fail. Okay. So you will need to address your mindset when you think about how to solve a problem. When you see your codes are very messy, then it's time to rethink about it before you continue to type. Okay. And the other advice I give you is that when you do your study, actually, it will pay off if you spend a bit more time to compare the programs that you have written in the exercise compared with the reference answer that I shows to you. And if you think that my design is a bit simpler, easier to understand, then you try to not hard memorize the code, but okay, explain to yourself why. Okay, the other design approach may eventually give you a simpler implementation. Okay, you learn from this experience, you learn from this comparison. Okay, how much you can learn is up to you. Okay, I can't change how people think. This part is very difficult. Okay, it's only yourself can improve by your own effort. Okay. There are two different types, two different comments that I have ever received from students in this course. Some say that the exercises are very difficult, and the other extremes is that some students told me that the exercises are too simple. Okay, so it is always the case that for this type of problem, you know the answer, the problem is always simple. If you don't know the answer, then the problem is always difficult. Okay, it's very seldom that there's something in between. Okay, it's either you know it, you don't know it. Okay, so, but in general, I would say that the problems are not difficult. Okay, this is on the easy side. Okay. So the important thing is that for whoever that thinks those exercises are difficult, then I would suggest you to go home and you do the revisions. Okay, since you have spent quite a bit of time on your own design, okay, then make a comparison with the answer that I showed you. Okay, and learn from your own comparison. Now, coming back to the notes. Last time we have started the discussions of binary search tree. Now, the binary search tree is a binary tree, okay, but there are some additional requirements, okay, on the properties of the tree. Okay. So the first requirement is that all the key values. The key values are the data fields that we use to rank the objects. Okay, so we call it the key field. Okay, so in the real-life applications, the key fields can be can have different possibilities. Like if we are dealing with student record, then the key field can be the student ID. Okay, or say the tax department, then if they are keeping record, then the key field will be likely, say in the case of Hong Kong, will be the Hong Kong ID. So it will be a unique identifier for every objects. Okay, then it will be used as a key field. Now in a binary search tree, the organizations of the data objects, okay, in the tree will satisfy, okay, those three requirements. All the keys in the left subtree are smaller than the key value in the root. And all the keys in the right subtree are greater than the key value in the root. Okay. And then the left and right subtree are also binary search trees. Now you see that very often in the case of binary tree, the definition of certain properties of the tree are recursive, like the one that the problem that we asked to solve to check if a tree is weight balanced. Okay, the same idea that when we define whether or not a tree is weight balanced, then the definition is also recursive. Okay, so when you apply to individual subtree, the same requirements should be satisfied. Now, with these properties, okay, then when you traverse the binary search tree using in-order traversal, then you will visit the data objects in ascending order based on the key field. Okay, so in the in-order traversal of this tree, the first node you visit will be 1, followed by 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so in a binary search tree, it allows the user to go through the list of items in ascending order. Okay, and it also supports a efficient search operation. Okay, so the search function is quite similar to binary search. Now, the search function can be implemented using iteration. Okay, here we use a while loop. Okay, to do the tree traversal. Okay, so we are searching for the value x in the tree. Then we define a pointer variable. We start from the root. Okay, as long as p is pointing to a weighted node, now we check if p is not null, then we will use the variable p further to reference some data value. Okay. Now if p is not a null pointer, then we compare x with the data at the node p. Okay. If it is equal, then we don't need to make further comparison. Then we can stop the loop. Okay. And if the function is required to return a pointer, then the answer will be p. Okay. Now if it is not equal, then we make one more comparison. Okay, so if x is less than the value at the current node, then we only need to search the left subtree. We don't need to search the right subtree because all the key values in the right subtree are greater than the key in the root, so we don't need to consider the right subtree. Okay, so we move to the left-hand side. Otherwise, we move to the right-hand side. Okay. So when we stop, we get out of the while loop. There are two possibilities. We have found the value. Okay, so the pointer p is pointing to the node that is storing the value x. The other possibility is that we have fall out of the tree. Okay, so p is now having a null value. Okay, so in either case, we only need to return the value of p. So if we design the function using recursion, for this case, the interface of the function is the same. Okay, we look for the value x. Now the interpretation of the pointer p means it is a pointer to the root of a subtree. Okay. Now you see that in the while loop we only require the use of the variable p. We don't need other parameters. So that's why in the recursive function we also need to provide the value of p. Okay. So if p is now in the design of a recursive function, once again, first we consider the base cases. Okay, so what are the possible base cases? So usually the first things to consider is whether or not p is a null pointer. Okay, so if it is a null pointer, no further computation required. We have an answer. So in this case, we simply return the null pointers. Otherwise, if the value in the current node is equals to your search key. Okay, the very next, then you have found it. Okay, then you return key. So if both cases are not true, okay, then you make a comparison and decide you will search the left subtree or search the right subtree. Now, in today's tutorial, I observed that some students, when they are making a recursive call, if the recursive function returns you a value, a result, then you need to make use of that result. Okay, if you don't save that result, don't use that result, then making the recursive call is meaningless. It will be the same that you don't call the function at all, because you ask the computer to do some work for you, it returns a result to you, and then I don't use it. Okay, if you don't use it, it is the same that I don't call it. Okay? So whenever the recursive function returns a value, you need to think about how to make use of that return value. Okay, so in this case here, we simply return the results of the search when we are searching the subtree. Okay. Now the advantage of binary search tree compared to a sorted array, okay, is that on average, the searching time on a binary search tree is order log n, comparable to the binary search of a sorted array. Okay. But the advantage of binary search tree over a sorted array is that when you perform insertion and deletion to the data set, the time complexity will, in general, the average time is also order log n rather than order n times. If you have a sorted array, you do insertion or deletion, the time required usually will be order n. Okay, imagine that in an array, when you insert something, that new item will be placed somewhere in the middle on average. Then you need to move half of the objects in your data set to put the new item into the array. Okay, so this movement of the data will consume order n times. Then the same for deletion. So if you delete an element in the array, on average it will be somewhere near the middle. Okay, the worst case is that you delete something at the front. Then you need to move everything, okay, in your array. Okay, so a binary search tree will give you the advantage when you need to update your data set. Okay, then the time required is also on average is order log n. Okay, so let's take a break first, and then we continue.